Hey, hello guys, this is Chintan. I work as a chief network architect at Broadcom. Actually, Ashay did order samosas, but then I requested them to cancel because I knew my session is just after snacks. So, sorry for that. Anyways, jokes apart. So, today I am trying to make a case for what we have been at Broadcom proponents of for a long time. Open and scalable systems which are standards driven for all kind of use cases. So, be it your campus, your CPU data centers, your GPU data centers, and now even your HPC kind of workloads. I want to make a use case which is kind of promoting Ethernet for all of these use cases, and we have purpose built products for each of these applications, right? And I'll take you through all of the products that we have for the same. So this is how we see networking for AI at Broadcom. You have a scale up rack or maybe couple of racks where you connect your GPUs, all the GPUs within the rack, and then you have your scale out where you connect all the GPUs within the data centers. Now, for most enterprises or smaller organizations, this should work, but then we have hyperscalers, right? And the kind of GPU clusters which are being built, one data center is not enough. They need to connect multiple data centers, right, to achieve the kind of scale or the number of GPUs they need for their applications. So then we have the use case of scaling out across multiple data centers. And for each of these, as I said, we have built products targeting each of these applications individually, right? So today I plan to talk about these three silicons which Broadcom has launched over the last 3 months. Looking at the speed of innovation we are doing, I think we are beating the speed of light, right? Tomahawk Ultra is where we focus on the HPC and the scale up use case. It's ready, shipping already. And then we have Tomahawk 6, which is targeting towards scale out. And then we have Jericho 4, which is what we are promoting for interconnecting GPUs across the data centers, right? Just that you have a look and feel. I've got samples of each one of these. So this is Tomahawk Ultra, which we have recently launched. Now, as I said, this is built to address use cases like HPC and scale up. So let me dive into features of each one of these chipsets and specifically Tomahawk Ultra now. So what you need for HPC and scale up, more or less, I would interchangeably use these terms because more or less a lot of the requirements for these two applications is kind of the same, right? So what you need is very low latency. The latency of Tomahawk Ultra is just 250 nanoseconds. Just 250 nanoseconds. This is almost half or 1/3 of the latency that you see for a regular Ethernet based silicon operating at this speed. It's a 51.2 terabytes silicon doing 64 ports of 800G, right? Now, with a lot of the silicons, what you would see is that though it can do 51.2 tera, but it cannot do for packets which are like really tiny in size. Here with Tomahawk Ultra, we can do like 77 billion packets per second. So if you have packets which are as small as 64 bytes, this silicon can serve. It is first of its kind. It has never happened in the history. It is first of its kind, directly targeting InfiniBand. Right? So you do not have an alternative. You did not have an alternative to, a lot of applications, HPC applications in particular, which required very low latency. But with Tomahawk Ultra, we can do that, right? And then you get all the advantages of Ethernet that you already use your monitoring system, the ecosystem, the knowledge base that you have in your organization. You can leverage all of these goodness of ecosystem that you are already using in your CPU, GPU campus, right? The same can be done, or the same can be repurposed for applications like HPC in your organization. Apart from this, we have added a lot of other features as well, right? What you are seeing is link layer retry, credit-based flow control, and I will dig into each of these features individually so that you get a gist of why this is the silicon which should be used for HPC or for scale-up kind of an architecture. Any questions so far? That would depend on your volume. Let's talk offline. Yeah, power consumption is more or less in line with our earlier chipset of Tomahawk 5. Yeah. So, yeah, we are proposing this for scale up and HPC with 250 nanoseconds. Just to give you a context of 250 nanoseconds, how fast or slow it is, right? So, if you were to blink your eye, it takes 250 milliseconds, and this is 250 nanoseconds. What it means is, by the time you blink your eye, it can forward 1 million packets. That's how fast this silicon is, right? So it is purpose built for HPC and then scale up. It can also do a lot of cool things when it comes to scale up kind of an environment like in network computation. Now, what is this? Suppose you have a collective operation where you are doing something like an all reduce. What happens is you have different XPUs, right? They throw out a number basically which needs to be kind of either summed or averaged or maxed out, whatever be the operation. Then if you have to do it in a kind of ring fashion, you can think of it as XPU 1 sends it to 2, 2 sends it to 3, and then you have a summation of all of them. But it takes a lot of time to do this. Here with in-network, what you can do is all of these XPUs, they send out their numbers to, or give their numbers to the switch, and the switch has an INC engine which can do it and then redistribute it to all the XPUs, right? Really cool. So it's no longer just a switch. It can also do a lot of your compute functions. Again, first of its kind. Third is link level retry. Now, with Ethernet, it was always abused that it is lossy. What we have done is made it truly lossless. What we can do is at the link layer, right? For every packet sent, you get a kind of acknowledgement. So think of it, if you had your regular Ethernet network, when you send a packet, if it is corrupted, the receiving device does a CRC check and drops the packet, right. Here what we are doing is, when I send out a packet, I check on the receiving end whether it is received correctly. So, between the two switches, if not, I ask the sending device to send the packet back to me, because I did not receive it in the right format. So, this function is introduced with Tomahawk Ultra. And last but not the least, what we are also doing is credit based flow control. So, it's synonymous to me asking the receiver, are you ready to receive, do you have the credit, right. Only if I get the credit, I send the packet. I just in regular Ethernet, what you do is you just send the packet, if the buffer is full on the other end, you just drop it. But here it is credit based, only if credit is available, you send the packet and then you get an acknowledgement as well, right. So, these are like really cool features where all of this reliability is built in at the link layer. You do not need to wait for the transport layer to come in. For a regular Ethernet, what would happen is you would send the packet and then your transport layer, whether it is TCP or RDMA, it signals to the sender that, oh, you sent 100 packets, but I lost these packets. Here we are doing at every hop at the link layer itself. Isn't it cool, right? So, yeah, these are some of the key features which we have introduced with Ultra, which makes it viable for, as I said, the scale up and also for your HPC use cases. Now, how did we achieve this? I will just double click on it before I move on. When you are doing scale up over HPC, or I would say scale up for the for a lot of the instances, what you generally do is it's only within a rack, right, or maybe multiple racks. So, this can do like 256 nodes for scale up. Now, it's generally, as I said, within a rack or multiple racks. Now, when you do this, what happens is you do not need a lot of features that you need in a regular Ethernet switch, right. So, those have been stripped off from Ultra, and that is how we have innovated. Actually, it is not innovation, it is like pure grounds up build for this use case, right, to achieve latency which is as less as 250 nanoseconds. Okay. Now, this is for scale up. I will move to our silicon, which is for scale out, again first of its kind, which is Tomahawk 6. Now, this is a silicon which is the first in the market to cross the threshold of 100 terabits per second, and this is 102.4. It can do 64 pots of 1.6 Tbps. Yeah, actually when I started my career, I worked on switches where the overall throughput was not 1.6 Tbps. Now you have a single pot which can deliver you 1.6 Tbps, right? And we deliver the switch in multiple kind of form factors. It can be 100G SerDes, 200G SerDes, CPO, all of these which are the need of the hour today. Now, let me take you through the benefits that you get when you deploy something as cool as Tomahawk 6. So, you can scale out if you have a GPU cluster as big as 128K GPUs. You can just build a 2-layer architecture and get done with it. You do not need to go to 3 layers. Now, again giving you context so that you understand how big is 128K GPUs. The total number of GPUs in India today is less than half of 128K, and I am talking about the whole of India, right? So if you bring in all the GPUs in India and want to form a two-tier claw network, you should be able to do it with Tomahawk 6. This is how powerful this chip is, right? Now, what are the advantages? Someone would argue, I can do 3-tier, why do I need 2 tiers? So let us understand that AI is a very intensive workload, right? You almost use it at 80%, 90%, 100% of utilization. And because of this, the heat generated kills the transceiver. No matter how good an AI cluster you build, you would see a transceiver failure rate of 1 to 2% at least. So the number of transceivers you reduce, or the connections or the devices you reduce, the more your reliability is, right? So if you build a 2-tier network versus a 3-tier network, you would use 67% less optics, right? The latency would be far less. Even if you take one device, taking about 800 nanoseconds of latency, if you cross 5 devices, it would be 4 milliseconds versus you doing, when you do 2 tiers, it's hardly 2.4 milliseconds. So the latency comes down drastically. The performance, obviously, because your reliability goes up, the performance of the cluster goes up, and the power consumed is much, much less. Now, the power is very important here, because that's a finite resource, and less power you spend on the network, the more power is available for your GPUs, which are very, very expensive resources to do the computation, right? So yeah, there are a lot of features again that we have added to Tomahawk 6 as well. One is, which I would want to emphasize on, is GLB. So with GLB, what we are doing is, now we have the full view of the topology and the traffic, right? So think of it this way, that you want to go from path A to B, and it's just like Google Maps, right? When you go from path A to B, you just don't look at the first road, that is, or the first lane when you want to exit. You look at the end-to-end path. With DLB, we were just looking at the first lane, the link where I want to place the traffic, whether it's congested or not. So if a leaf wants to send the traffic to another leaf, it would just check, okay, which is my interface, which is free, where I can place the traffic and send it to the spine. But now, what you are doing is, you are checking an end-to-end path from leaf to spine to another leaf, right? So this we had it in Tomahawk 5 as well, and now we have the version 2.0 in Tomahawk 6, and then DCN, fast link failover. So a lot of cool features which we have added just to make scale out possible, right? In the interest of time, what I would do is quickly move on. If you have questions on any of these features, we can discuss it. What we are seeing is, the number looks very big, 1 million. We are seeing hyperscalers already crossing 100,000 GPU marks, and when they're building clusters which are this big, they are running out of power, space within the data center, right? So it mandates them to kind of expand their data centers, or have multiple data centers and then interconnect them. So we have a chip for that as well, which is something which we just launched last month, which is Jericho 4. And again, it's first of its kind. It has a 3.2 Tbps hyperport, right? So when you want to connect two data centers, you need real high bandwidth, and Jericho 4 has a 3.2 Tbps hyperport which allows you to do that. Apart from this, another very cool thing which I would want to touch upon is it can do line rate encryption at this high speed. So when you are exiting your data center, you are going through some kind of public infrastructure which you would want to be wary of, right? You would want to secure your data because it's going over public infrastructure, and that is where this line rate encryption at such high speed really comes in handy. So yeah, this is all I had from the silicon point of view. Now coming to the call to action, we at Broadcom can build great chips, but we need support from the community to enhance SONiC, right, to kind of leverage these features that we have on the silicon. So my request to you would be to build or enhance SONiC for scale up, scale out, and also for scaling out across multiple DCs. Thank you. I'll end it here. Any questions?
Do you have a question?
Okay, I got it first.
Yeah.
Okay, a lot of speed. Now, in one of your slide, it was mentioned optimized Ethernet.
Yeah.
Yeah, can you give us a little bit of an idea? What is that?
Yeah. Sorry, you are from?
My name is Kingshuk and I'm from Keysight.
Yeah. I was just checking you're not competition. Anyways, jokes apart. So, no, a regular Ethernet header with IP with UDP header. So an Ethernet header is like 18 byte. The IP header is 20 bytes and the UDP header is 8 bytes. So it makes 46 byte of payload. Now when you use it for scale up Ethernet, you need not necessarily have all of these headers in place. So we have come up with a specification called as SU, which is called scale up Ethernet, which helps you to reduce this to 10 bytes, right? So you can have 3 bytes of source MAC, 3 bytes of destination MAC, 2 bytes for the kind of packet it is, and 2 bytes for something which are missing. So basically you shrink the header to 10 bytes, and with this 10 bytes you can actually use it more efficiently, right, within the rack, because it kind of curtails the payload that you have. I would say that for a smaller payload also, otherwise where you would need 46 bytes, here you would need only 10 bytes. So it kind of curtails the overheads and makes the system more efficient.
Yeah. Just a comment that Ram said like 4 weeks ago that you guys can go to 400 nanoseconds on the scale up. So
yeah.
Basically, so there's no need for UA link at least for it to run, because it's available now. Where UA link said, hey, at the end of next year you're going to get 400 nanoseconds. You say, hey, I have it here. So Ethernet is going to win again.
Okay. So now reducing on a header, say from 46 bytes to 10 bytes.
Yeah.
Given our payload here will be mostly around 4096. If you think about
depends.
trend.
It depends.
Okay.
It depends whether you are using it for HPC or whether you are using it for AI. So basically it depends on the application.
Okay.
Yeah.
So in what kind of application will benefit from it?
Yeah, basically it's for scale up, okay, and that is where it is specifically mentioned, it is for SU. So what I understand, I get your question that 4096 versus 46 is not that big, right? So you can certainly go ahead with 46. This is you move to 10 bytes if you want to optimize it even further.
Okay.
Yeah.
Thank you.
Okay. On the link layer retransmission
Yeah.
that you mentioned, right? So within scale in and scale out, I'm assuming it is surely supported. Across the regions in Jericho 4 also it is there, or across the regions it does not apply?
Okay, so primarily the use case for that would be, I would say, where we use Tomahawk Ultra, right?
Got it.
And that is where we are supporting it as of now.
Okay, thank you.
So this is Vijay from Nextop. So my question is, Tomahawk Ultra, I think it's using SUE, you said SUE, right? The scale-up Ethernet. So you talked about lossless retransmissions because it's credit-based. So I was just wondering, at the link level, are you putting some buffers or some credit mechanism, or how does, is it like, are there any packets in flight when the corruption happens? So is it, meaning, I'm just wondering about link level, how do you ensure lossless?
So think of it as first you are assigning credit. So if I give you credit, only then you are supposed to send me the packet. And until I acknowledge the packet that you have sent to me, you are not going to discard it out of your buffer.
No, that particular packet, but are you going to send any other packets, or is just blocked?
If I have given you 10 credits, you will send me 10 packets, right? And while sending the 10 packets, if one of the packet is corrupted
Correct.
in path,
Yes.
that is where the link level retry would come in, and I'll say, oh, the packet number 5th was corrupted, send it back to me. And because you are still holding it because I have not acknowledged it yet.
So there is some buffering that is
Yeah,
happening.
yeah,
That's what I want.
Yeah. I mean, credit is buffers.
Yes.
Yeah.
Any more question? That side? Okay.
Yeah, I
No,
can hear you.
Yeah, use the mic. Introduce yourself.
Yeah, this is Jimston from Celestica. So I'm just interested in understanding the link layer retry, right? This link layer retry and credit-based system are not linked, right? Shall I assume that link level retry is a separate feature?
So okay. So if you look at the UET specs, right? It says that these are capabilities which are negotiated individually at LLDP layer, basically with LLDP. So you negotiate whether you want to do a link layer retry, you negotiate whether you want to do a credit based flow control.
Okay.
Yeah.
Given that, if you keep aside, you want to add up something?
Yeah.
Yes.
But what I would say is they can work individually, but if paired, they do a better job.
Okay. So my question is, when using link layer retry as a standalone feature, right, without the credit-based thing, I'm just trying to understand what will be the impact on the bandwidth. Because for every packet, you're sending an acknowledgement. That is, I'm using the RX path as well.
Yeah.
Okay, so how you will be able to support the extra information that is being fed into the line, right? At line rate
Yeah.
is my...
Yeah, but
question.
you can still go at line rate. It has nothing to do with that.
So...
So basically,
No,
what you were
no,
trying to tell me
okay.
is, or what you were trying to ask is,
how is this
if
extra...
I use this feature, can I go at line rate?
No. What my question is, some extra information is exchanged between the two peers, right?
Yeah.
But the optics, the transceiver, the cable that can't support extra bits beyond the confirmed line rate, right?
Yeah.
So how this information is being exchanged, or the acknowledgement? When there is line rate duplex traffic that is going through the line,
Yeah.
how this acknowledgement bit is sent? Because that is something over consuming the bandwidth, right?
Yeah. So what you are trying to tell me is that the effective payload would be curtailed, right? Yeah, that's a penalty you take. But then what it brings to you is reliability, right? See, if you don't have this, just think of it as if you don't have this, With today's RDMA, you go back n, right? If you are sending me 100 packets, if the 5th packet is dropped, with today's RDMA, what I am doing is not just, you just don't have to send me packet number 5, you have to send me 5 to 100. That's the limitation with today's RDMA. Now, when you are doing this, right, you might take that minor penalty of dropping, your payload, which you would have earlier transmitted at 51.2 versus now, but that adds a lot more reliability.
So there is a trade-off, but it's a minor trade-off.
Yeah, obviously.
Okay.
And again, all of these are optional features.
Yeah.
I mean, if you don't want this, if you want to use the regular Ethernet the way it was being used, you can.
Yeah. I'm just trying to understand.
Yeah.
And also the latency will be a trade-off, right? Minor latency because of the acknowledgement and then sending the next packet.
Yeah.
Because it adds line
See, I don't
latency.
think so. See, think of it this way. A packet drop is dropped, right? If you didn't have this, you would anyways had to resend it.
No, I agree. Yeah. Because that is a great,
In fact, you would have to resend it 4 hops away or n hops away. Now you are doing it at that layer itself. So it cuts down the latency.
Yeah. Okay. Thank you.
So, Chintan, sorry, coming back on my question, right? When you said Tomahawk Ultra is what is targeted for this.
Yeah.
In case of scaling, there's practically one switch, apart from redundancy, there's one switch connecting to servers, right?
Yeah.
In case of Tomahawk Ultra.
GPUs, yeah.
And all the GPUs are talking to Tomahawk and then coming back to GPUs. So, there is no switch-to-switch communication for this feature to really be effective.
Yeah, but it depends, right? I mean, tomorrow you can have NICs which can support these UEC features, and then between the NICs and the switch also you can negotiate this.
Got it.
Yeah.
Okay.
Hey, hi.
Yeah.
Hey. Hi, this is Ravi from Marvel. Hi. Okay. Nothing competitive, but just to answer, right? And by the way, great talk as usual. Okay.
Yeah.
And just to answer about the LLR inefficiency.
Yeah.
The acknowledgements that the receiver sends to LLR, right? They are not really a full packets. They are the control ordered sets.
Right.
Just encoded in the regular synchronization mechanisms, right? That's one. And also, they don't send acknowledgements per packet. It's sent periodically. It's configurable, and for n packets, right? You can send just one acknowledgement, and that is also not part of the full Ethernet packet. It's just control ordered sets. So that's how the Ultra Ethernet transport has been defined.
Yeah, he's bang on, and that is why I said the penalty is very, very minimal.
Yeah, I don't have a question, but a couple of points to make, right? One is there are multiple techniques, you can use preamble and, there are many ways you can compress the headers to get that extra bandwidth. So we need to keep that separate, right? But that's one comment. The other one is I saw somebody saying scale in. So there is a terminology that, a bunch of us are trying to push. Manoj Wadekar at Meta and me, we're trying to standardize something, at least. Scale in is kind of looking inward, chips and chiplets and whatnot. Scale up is within whatever rack. Scale out, there is a scale across. I think going forward, you may want to use scale across for Jericho. Just take a, it's very hard to keep up with AI. Every week is new, right? So and again, the reason for again saying it here or somewhere else is that, if we don't have the right terminology, we are talking about the same thing, but we are in two different worlds, right? So think of scale in is inward scaling. You see many of them doing at a, wafer level scaling and chiplets and whatnot. So a bunch of techniques being used there. And I think somebody used scale in for scale up. That's why I'm trying to, again, it's not wrong. That was the terminology different worlds were using. Let's standardize that. And I keep on going back to LinkedIn and keep pushing something so that it becomes standard. Scale in, scale up, scale out, scale across. Jericho is scale across.
Okay.
I'll talk to Ram later to see, or whoever it is, right, to
Thank
fix
you.
that, right? Thanks.
Cool.
Any
Great
other
topic.
questions?
Anyone? Oh, yeah.
Chintan, yeah, thanks a lot. Again, coming back to LLR, is it for the integrated PHY or external PHY, or which layer we are trying to identify the error? to raise, retransmit from the far end.
Sorry, I would not be able to answer this.
We have 5 contains several layers, right?
Right.
From PMA, FEC, PCS. So Tomahawk 6, where it detects the error and tries to opt for this solution, recovery method for the integrated file. If it's an external file, if you want to really read FEC errors, then you need to go to the other chip and read.
Yeah, maybe this is more from the hardware perspective. I'll check on this and come back. Yeah.
Thank you.
Any other questions?
Hello? 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 Cool. I think it's working. Okay. Great topic. Any more question? Anyone? If not, thanks a lot.
Thank you.